What I'm saying, right? Because now it's being recorded. It has very limited effect on me. All right. Good to see everyone here. We've had a long and very warm summer break. We hope that we're going to get more frequent events coming up over the next couple of months. Before we hand over to David and Meltwater and then Joseph, we just wanted to say a few words about the Meetup group itself. So some of you are familiar with Jakob and me and some others here. We have this spring hosted a conference called Gaia. This was kind of an effort to build like a huge meetup because there's usually a lot of oversubscription to the events. It was successful enough, as far as we can tell, to merit doing it again. So the plan is to do it again in April 9. But it turns out it's easier to do these things if you have a slightly more formal entity around it. The credit value of 5 friends is apparently not high.
Not even 6 friends.
6 friends. Doesn't make much difference, I think, in credit-wise. So we want to form a nonprofit, an ideell förening, for those who know what that means. And that means we're going to put together a board. And that board is going to be the hosting committee or the sort of organizing committee for Gaia. So that sort of merges the meetups with Gaia and forms a little entity in a nice way. So we invite everyone who's interested to be part of this. And we're going to have our annual, or rather, I guess, creational, what do you call it? Formation meeting. It's not really annual when it's the first time, right? Our annual meeting on October 2nd. It will be advertised as a meetup event, but it's really mostly going to be forming the little organization and then, I don't know, drinking beer. Maybe there will be someone talking. I'm not sure.
Who's going to work on the statues?
I've actually been assigned that, or I guess I self-assigned it.
Yeah.
Yes. Right. Yeah. Good. I think that's about it. If you're interested in this, you can talk to us throughout the evening, and then try and make it on October 2nd if you want to be either voting or being elected to something. We can probably make up a title if you want. With that, or did I forget anything?
Maybe we could say that we plan to use the Gaia name for the meetup.
Oh, right. Yes.
That would be a change. So
we're unifying our brand.
Yeah.
Sounds cool when we say.
Yeah, brand strategy.
Yes.
That's where we started.
Yeah.
You can call it the Gaia Support Association.
Gaia Support?
Yes.
Got a nice ring to it.
Association that many organizations do that.
All right.
Even companies.
All right. Yeah.
Make it easier for them.
Thank you. We'll figure out a name, and then we'll see you on October 2nd. With that, we'll go over to the more important things. So thank you for hosting us, first of all.
Thank you, Daniel. So welcome to Meltwater and this meetup. My name is David Burke, and I'm part of the information retrieval team here at Meltwater. And we run and build services on top of a very big Elasticsearch cluster with about 40 billion documents. And this forms the core of Meltwater's suite of products that allow our customers to search and analyze and monitor online media, so editorial media, social media, to try and gain insights on how about their company, about their competitors, about their market. And in the past couple of years, there's been a kind of an extra emphasis in Meltwater towards trying to leverage AI to make these products smarter, to get even more insights for our customers and provide more value for our customers. And for our team, for our information retrieval team, that's meant some interesting use cases like predicting query times, producing recommendations, personalized recommendations of documentation of documents to show customers. And another example is clustering documents, similar documents together to build storylines over time. So we have a lot of interesting use cases we can do with this big Elasticsearch cluster that has some interesting machine learning problems. We're also expanding, and today with a few open consultant positions. There's also full-time positions opening up from time to time, and we hopefully will have maybe a master's thesis coming available in the next couple of months as well. So if anybody has any interest, just let us know, and we'd be happy to talk to you. So this meetup, this is part of us continuing our own competence improvement and our own, I guess, becoming a bigger presence in the machine learning and data science community in Gothenburg. And so it's exciting for us to host the event, and welcome again. And now I pass over to my colleague Johan for the first talk.
Move this one down a bit. Yeah, thanks. Let's see. Okay, is it full screen, or is that because of me?
I think it's as full screen as it gets.
Okay, yeah. Okay, we can see it on both.
Okay, perfect.
Okay, cool. Hi, everyone. My name is Johan Nilsson Hansen, and I work here at Meltwater as a software engineer. And I'm going to give you a short presentation on how you can optimize your neural networks using genetic algorithms. And the agenda for this presentation will be roughly as following. It will take about 15 minutes in total. And I'm going to start with giving you a short introduction into kind of what the problem we're trying to solve here is. After that, I'm going to tell you a little bit about what genetic algorithms are, and also how you can use them for neural networks. After that, I'm going to talk a little bit about what kind of outcomes you can expect from using this. And we're going to end with a short Q&A session. Yes. So introduction, what is the problem that we're trying to solve? So after you go home today, after hearing the next presentation on deep recommendation systems, you might want to go home and try to create something of your own. Like create a network, train it, get some results, right? But after a while, you're likely to come to a point where you ask yourself, I wonder how I can optimize this network further. How can I change the architecture of the network to make it improve my results? So a brute force kind of way to do this would be to just list all the different things you want to try out. I want to try out with this many layers and this many nodes in the layers, and which activation functions to use. Yeah, whatever. Or you can come up with a lot of things, and then you just try out all the different combinations of those. And this will give you the best result, or the best network for your specific problem. But however, that will be a huge, or will probably be a huge search space. So it would either be very time consuming or very costly, or maybe even infeasible to do in practice. So what we're trying to solve in this presentation is how we can get good enough results in much faster time. Yeah, so what is genetic algorithms? So genetic algorithms are inspired by biology and mainly survival of the fittest. And in survival of the fittest, you have a population of individuals, right? And each individual is composed of a slightly different set of genes. And these genes makes you more fit to certain environments or less fit to some other, right? So some individuals are more adaptable to some environments and some are less adaptable to that environment. And this gives us so that the more fit individuals have a higher chance of surviving, and thus they have a higher chance of breeding the next generation. And the individuals who are not very fit to that environment are more likely to die and get extinct. And this is kind of the key thing we want to capture in the genetic algorithms. We want the good things to stay alive and breed hopefully better things, and we want the bad things to die out. So how can we use that for neural networks? Well, we start kind of in the same way that we did with the brute force way. We list all the different things that we want to try out, and we create genes for them. So we have one gene that determines how many layers the network should have. We have one gene that determines how many nodes each layer should have, and then one node, yeah, for whatever kind of, everything you can come up with, you create a gene for that decides how it should be. So this will be our gene pool. Yeah. And then the algorithm works as following. So you start with randomly creating a population. So from this gene pool, you just randomly pick stuff from it, and then you create networks from those genes that you get. So you start with a random set of neural networks. These are individuals. And then you want to find out how good they are. Which one are the more fit ones, and which one are less fit. So you need a way to score them. And using neural networks, it's very convenient to use the validation error of the network. So you train it, and then you check how good it performs on your test data set. And the better it performs on the test data set, the more fit it is to that environment. So after that step, we have a score for each network. Which ones are the good ones, and which ones are the bad ones. So then what you just do is you pick the most fit networks and let them breed. And breeding in this case, you can do this in many different ways, but an easy way is to just randomly pick one gene from either father or the mother. What you also might want to do is to randomly mutate children. So this is kind of done to avoid local minimas or maximas, depending on what you're optimizing. So you get a little bit more of a more diverse population. And once you've done that, you kill off all the networks that didn't make it to the next round. So the next generation would kind of be the parents of those that got to, the parents, the ones that got to breed, and their children. And then what you just do is you kind of repeat this. So you go to step 2 again, and just repeat this for either X amount of step, or when you reach some pre-specified threshold that you kind of decided on beforehand. Yeah. So by using these kind of algorithms, what can you expect to get? The first thing you get is a winner network. In the end, you will have this is the optimal, or the best thing we could produce using this algorithm. But that's not the only thing that you get from this, because you also have lots of information in how the population evolves. So you can also kind of see dominant genes throughout the generations. And I have some slides here for that. So, that was a bit laggy mouse pointer. But on the x-axis, you have which generation it is. And on the y-axis, you have how frequent a gene was in that generation. So this is an example where you can see the number of neurons in each layer. And we can kind of see here in the beginning that it's a little bit random. But then after a while, you can see that at least one gets really, really dominating. So that is a quite good indication of that's a good parameter for this specific problem. We can also see that some genes completely die out here. After step 6, there are at least 2 that die out. But we can also see them reappearing here as a mutation in some generation and then dying out again. I have also another example, but I guess it's roughly the same. So you have a bit more random here in the beginning, but then after a while, you can kind of see which ones are the good ones. It's not always that obvious, like these graphs show, but it's kind of interesting information that you can find from this. And also, the key thing from this is that it could be magnitudes faster than just doing the grid search through all the different combinations. The speed is somewhat tweakable. You can tweak how many generations you want to do. And you can also tweak how many individuals you want to be alive in each generation. So you can kind of customize how long you want to wait for an answer. The longer you wait, the better the result, or the more likely you are to be near the optimal, but you will also have to spend more time. So it's a trade-off. Let's see. I've included some resources here. I'll make sure to make the slides available afterwards. So if you want to read up more about this topic, or if you want to try them out yourself, these both have information and code included. So you can just download and run something for yourself. And that was everything I had. Thank you for listening. So any questions?
Do you use the same testing and training data sets for each generation?
Yes, that I've done, yes. But we've used it in a kind of k-foldy way, so you try out lots of different data sets at one, and then average the results.
Isn't there a risk that you optimize for this particular data set?
There is, yes. So the outputted winner network might not actually be it might be slightly overfitted, but that's when you can look at the generational graphs and see kind of which are good features. So you can take more, you can get like a feel for what's good for your network. So you can use that to create something very good instead.
There is also a fitness function, right?
Yeah.
You did not.
So the fitness in my case was, I'll go back. Let's see. So here, the fitness function would be step number 2 here, where you score each individual. That's what's determining your fitness.
So it's like mean squared error or something like that.
Yeah, I mean, depending on your problem. But yeah, we did a regression problem, so we used MC, yeah.
So it only works for supervised
Ooh,
learning.
that is a good question. I would guess so, yeah. You would have to, at least you need some way to benchmark it. You need some way to score them. That's all you need.
If you have an unsupervised problem, you can use a likelihood function.
Yeah.
Also, reinforcement learning, there is some work, for example, in Uber. Other cases.
Yeah. Yes.
So how much faster was this than doing a grid search?
I don't remember how long it should have taken. The full run for us takes about a week. We get good results after about 4 days. I don't remember how long the original one would take, but I don't know, say a month, maybe something like that. But it's very tweakable, and you can kind of customize it how long you want it to take. We kind of decided that we had that much time, so we spent it. But I think you can get results much faster than that if you really want. Yes.
So what made you pick this one? Because I guess there are other hyperparameter tuning algorithms which are famous.
Yeah. Mostly because of the simplicity of it. It's like these steps are not very hard to like encode in programming. So it's like, I don't know, 200 lines of Python or something like that. So it's very easy to create something for yourself, and it's very easy to like get a feeling for what happening. That's the main reason.
I guess the problem here is that you will introduce genes randomly that you know will never produce a good model. So you spend a lot of model training on bad genes.
Yeah, you potentially, yeah. That is definitely the case. Yes?
Thank you for this presentation. So I have a question regarding the parameters that you encoded. I saw that some of them were categorical, like choice of activation function and weight initializer. And like optimizing categorical variables in general is a very hard problem because you don't have any relationship between them, or not necessarily. So did you take any like specific? Did you consider this at all, or did you let the algorithm do its thing?
The latter thing, I let the algorithm do its thing. Mostly because I'm also kind of new to machine learning, so I have very hard, like reasoning about stuff is kind of hard for me at this stage. So it was very easy for me to just throw it in and let it see what it produces, kind of.
Did you find that the optimization converged towards like the same kind of architecture for multiple runs, or did it produce like different results?
It produces, depending on how what like similar means, but they produced some different results. Some for like layers and nodes, we got kind of the same thing during, I don't know, 3 different runs. The other ones are a bit more random, it feels like. They're probably not random, but it's not the same in each run. So you can get different results, yeah. Yes?
So when you get one of these networks, how do you know when they're done training? Do you train them for a fixed number of epochs, or do you have some kind of early stopping?
The best way would be to have some like what was it called, early stopping callback, whatever. So you have something that stops training when it's like converged. That took too much time for us, so we just had a predefined amount of steps for all networks. That's how we solved it. But the optimal would of course be to have something that lets them train until it converges. Any more question? Yeah.
When you have the mutations, do you change some parameters or only change them between the initial values of the set of original genes?
You can do both. I only picked, so when I mutate, I only pick stuff from the original gene pool. But you can do like averaging, you can create new genes if you want. That's an option as well.
It will require maybe more combinations and maybe if the parameter of fitness has to do, well, if it behaves in a monotonic way, well, it would be easy, but if it doesn't behave monotonic, it's going to be a huge problem.
Yeah, yeah.
Okay, thank you.
Yeah, thanks.
Did you spend time in arranging crossover? Did you work with crossover in this algorithm?
So crossover, not as in breeding, or no?
So when you take 2 genomes and you cross genes between, so in some cases people use also crossover, then you have crossover rate and mutation rate.
Okay, but okay, so what's the difference between crossover and breeding? Sorry.
Well, you can. I'm not sure. It depends how you implement this. So you breed the network using crossover. So you took genes and you.
Yeah. So when during the breeding phase, you just like randomly pick stuff from the either parent. Yeah. I guess that's what is called a crossover. Yeah. So that's how we've done it. Just picking a random gene from either parent. And then also mutation on top of that. So that's the 2 things we have. Yeah. Anything else?
Thank you again, Johan.
Thank you. Let's see if I can.
Okay, so how? Hi, nice to see many new faces here today, and almost a full room. I'm Joseph. I work as a machine learning consultant. I have been part of this group since the beginning, probably. And today I will do something I haven't done before, which is present directly from Jupyter Notebook. So I'm a little bit nervous about that. And this meetup is a continuation of the last meetup we had before summer on recommendation systems. And I had too much material planned for that one. So we decided to break it up into 2. And on the first one, we did, shallow machine learning, or linear machine learning in some sense. And today we're going to continue with that to do deep or non-linear extensions of that. And I will base the talk on a paper by some Netflix and Google people and some guy from MIT. It's Dave and Liang et al. On variational autoencoders for collaborative filtering. And it's basically a copy of their TensorFlow notebook that they published together with the paper that I ported to PyTorch and adapted to the data set that I discussed before summer. And I hope that this talk will be sort of, you don't need to, there's no requirement that you were part of the last meetup, but there will be some overlap as well. But if you have any questions, of course, tell me, and I will remember to repeat them so they will be in the microphone for the people online or that will watch this later. Yeah, so it will be starting with the imports. This will be based on PyTorch, and then pandas for handling the data. And then for the last meetup, I used a package called LightFM, which is an implementation from Lyst. It's a UK company of something called factorizing machines, which is a model discussed at the last meetup. You don't need to know about that now, but we will compare the results in the end. And then NumPy, of course, NumPy. So those are the packages that we will need. And let's see this scrolling here. So I have imported one of the slides from the last meetup, just as a picture into the notebook. But the idea here is that the data set I picked was papers from the archive on the stat tag. So found a scraper that could download all the papers from 2008. And the recommendations that we're going to make is to recommend the professors from the stat papers what they should write about next. Okay, so that's the idea here. I mean, it's always fun to introduce a data set that you can create yourself from data that is available online. And the data that you usually work with might be secret and so on. So that's why I decided to do this. So, and here are some professors that we can eventually recommend topics for them to write about when we have built our recommender system. So that's the sort of the goal we have. And the scraping was done last time. The code is available on Bitbucket, this repo. But it's basically all articles in the stat category from 2008 until I updated the dataset now. So it's until the 14th of August. And I have divided it into a training set and a validation set. So all the articles up to March would be my training set. And then from March and so until now will be my validation set. So this is how the data looks like. So in recommender systems, you have users that you want to recommend items for. So that's basically the basic framework. And in this setup, I will have the users are the authors. So this will be Eric Young, Martin Reed-Miller, Roland Hafner, and so on, people that have written articles in statistics. And the token will be words in the title of the paper. So for example, from end of February this year, Eric Young wrote about something vision-based. And then we had Martin Reed-Miller wrote about something sparse. And then we have a lot of people that probably were on the same paper. So we count them, all of them will have written about sparse. So that's part of their item history. So this is how the data looks like. So now we're going to use this as build a recommender for that. And I want to laser point, but I can do it with the mouse maybe. So this will be some math here, kind of math heavy, but because these variational autoencoders are kind of math heavy technique, and I hope you're familiar with the notation. Otherwise, just ask, and I will explain. So we'll let zoom in. Yes, absolutely. Is this better? Can you, okay, this is too much. Oh, it's lagging. This is good, maybe. So XU is the vector of counts for all the tokens that an author has a professor has written about. So we will have one vector for each professor, and they will have ones for all the tokens they have written about. It could be deep, scratch, sparse, and so on. And it will make it atemporal, so it will not depend on time, but it's up to a point t, which in my case will be March. And then I will, so this conditional probability is sort of what the goal of my recommender is. I want to predict what the probable next token an author will write about. So this is, X is the variable of your choice of word in the title, U is the professor, and then T plus 1 is the, in the future. I want to predict what's going to happen in the future. And then I want to, what's the probability of it being some item K in my list of items. And this probability will depend on features that are known for the professor, features that are known for the item, and then your history. So this is just the most general framing of the problem. And in collaborative filtering, which is sort of a standard approach, is that you skip the user and the item features. So it will only be based on the history of items that you have purchased, or that's for item recommendations in an e-store. But in this case, it will just be based on the topics of the papers that you have written. So, and that's collaborative filtering. Content-based is the opposite. So I will skip your history and only work on features that I have on the professor and the token. So features in this case could be, for example, your university affiliation, your age, and so on. When did you start working in the field, and so on. That's the features we have. And if I'm using some combination of these, it's called a hybrid approach. So this is the most general formulation of the recommender problem. And today we're going to do collaborative filtering, which is basically that we skip the features. We'll only use the histories. And this is done classically with something called matrix factorization. And this is equivalent. So I have, I construct a matrix with all my users as columns and all my items as rows, and I put ones and zeros where for items that a certain user has chosen. And then I try to factorize this matrix into some embedded space using some embeddings. And so they become vectors in this embedded space according to this formula, and I take the scalar product between these two, and I get what's your propensity to write about this item, to purchase this item, and so on. And this is the equation. I have my embeddings, and I take the scalar product in the embedded space, and that's the probability. I will have to normalize this in some sense, but that's my estimation of this conditional probability. And I did some visualization of this for the last meetup. So this is my matrix, Rij. That's my user item matrix. And I factorize this into some user matrix and some item matrix. And I try to minimize the error when I try to multiply these two. So the inspiration here is some singular value decomposition or something like that, if you remember that from your linear algebra courses. But for example, Jan LeCun, he's a stat professor, written many articles on statistics and deep learning and neural networks and whatever. And he becomes a vector in my embedding space. And for example, clustering is something you can write about when you write the statistics paper. It becomes a vector in this embedding space as well. And I reconstruct my user item matrix by taking the scalar product with all these combinations. So that's just classic collaborative filtering, matrix factorization. And the interesting thing about this is that if you had a perfect factorization, you would not have gained any information, because you will just reconstruct exactly the user item matrix that you had to start with. So actually you want this factorization to be slightly bad. So you actually gain some information. So you have entries, non-zero entries where you didn't know anything about what the professor thought about this topic.
Question.
Yes.
So this product also consists of lots of scalar products, and you have the scalar product above. So is it like the same thing or related?
No, it's the same scalar product.
Okay.
Yeah. So it's just a different way of. I mean, I can write the matrix product as the scalar product with all these different vectors in
So
the
you
matrix.
can see this R matrix as for every user they have picked a set of tokens, and this is like a distribution of. It's the same distribution as the P we have here.
So that will be each column if my rows are the users. Yeah. So now we're going to. I wanted to mention this because the scalar product, because that's a sort of a linear way of describing the relationship between my user and my authors and my items. And we're going to generalize that with a neural network now, eventually. So let's just see how this looks when we create the data set in Python. So I will start with, in pandas, to have my training set, I will group by token and author and calculate how many times a certain professor has written about a certain token. Sorting here. So David B. Dunson, for example, he has written about Bayesian 33 times. And then we have Joshua Bengio, for example. He has written about networks 24 times. And when I make this into a user item matrix, that will be 24 on the column and the row where he's just a combination between network and Joshua Bengio. That's so far so good. Right. Note to self here. Remember to explain why the model below. So when I did this recommendation project in the spring, I started with, shallow models, and I wanted to try some deep models. People tell me every day, why don't you try deep learning? So I had to try it, and I tried a method called neural collaborative filtering, which is that you have these embeddings. They become exactly like word embeddings for word2vec, for example. And then instead of taking the scalar product in the end, you put the multi-layer perceptron in the end to generalize the scalar product. And that's called neural collaborative filtering. It was one of the first approaches that people tried to do these recommender systems, but using deep neural networks for. And I tried that, and I didn't get that good results. And I had kind of good results with my non-neural based methods, so I didn't want to spend more time on it. But then for this presentation, I decided since this stuff didn't work, I wanted to try something new. So that's why we're doing autoencoders today. And I think it was a good decision, actually, because I got much better results from that. But we're getting to that.
Is that how people generally find these more sort of nonlinear approaches behave? Or
I think it completely depends on the size of your data. So
more sort of under I'm guessing the less data you have, the worse deep learning performs. Right?
Yes, exactly.
That's
exactly. Yeah, exactly.
It's dumber.
Yeah, it's yes. Yeah, it's sort of a brute force method for learning. Yeah, absolutely. Absolutely, and we will see that in the end, but I don't want to skip ahead. But basically, you only have non-linear structure in your data when you have a lot of data, or a certain problem where it's inherent in the problem that you have some non-linear structure that you need to pick up with some deep net. But no one has really the intuition here. I think that's one of the problems. So let's go take a step back. Before we do that, okay, I introduced the collaborative filtering approach. Matrix factorization, only the history of the users are important, and we make this matrix with users on as columns or items and as rows. Okay, that's that. So let's take a step back and think of an abstract problem. So I have a very general graphical model with some hidden variables. So I have some px that depends on some non-observed stochastic variable set. So let's say we want to infer income of the owners of cars, but we only observe the car. And I don't observe anything else than the car that people drive, but I want to sort of estimate the income. The car is my x, that's my observed variable, and I have some latent variable, some hidden unobserved stochastic variable called set. I can write this as the conditional probability of x depending on set. And in my case, if I want to rephrase the collaborative filtering problem, x is the click history, and z is the embedding of click histories into some latent space. So if I want to do posterior distribution estimation here, I want to estimate the probability of z's giving x's. Just normal, Bayesian analysis. What, sorry? No. So most likely, this is an untractable problem. In general, it is. Even reasonable approximations lead to untractable problems. So, I mean, in the classical Bayesian framework, we solve this brute force with Monte Carlo sampling in like programs like STAN, PyMC3, and so on. But there is also this method called variational inference. And that's another way of solving this problem. And that's implemented in frameworks like PyMC3 and STAN. Automatic differentiation variational inference, ADVI, some fancy new stuff people are doing. I don't want to scroll too much because you will be super confused about all the stuff that's coming afterwards. So in variational inference, what you're doing is that you're introducing something called a variational distribution. Make up something called Q, should be Q set, and that will approximate my posterior distribution. And if I assume Q to be easy enough, I can make the problem tractable. Okay. I can calculate a lot of stuff with it. That's basically the idea. And I want to approximate my variational distribution as closely as possible to the proper posterior. And so in this very famous paper from 2013, two guys called Kingma and Velling, that's from Europe, so we're all happy about that. It's not too often. So basically, they described how to do this with a neural network. So we approximate the variational distribution as a multi-layer perceptron. And I mean, they frame it in the autoencoder framework. And if you think of an autoencoder, that's something that encodes a message and then decodes it as well and try to reproduce the message that you started with as good as possible. So in my probabilistic framework, this is equivalent to the decoder describing the posterior and the encoder the likelihood. And if you remember your Bayes theorem up there, the posterior is a function of the likelihood and the prior. And then you normalize it with the likelihood of your, or the probability of your data. So now we want to use this for collaborative filtering. So the model that the Google guys introduce, it's this one. You start with your, in my case, it's the history of articles that your professor has written about. That's my X. And then I approximate the variational distribution. I approximate the posterior with a Gaussian, a multivariate Gaussian. So the Gaussian is described by some mu, that's my mean, and some sigma, which is my standard deviation. And then I try to, my Z, which is my latent variables, would be a function. It's normally distributed with these parameters. And then I have some model for how to reproduce the x out of the set. And this is the equations for that one. So z is normally distributed, and then I have x to be multinomially distributed from the probabilities I estimate from the latent variables. So there's a lot of information here right now. I noticed that. It's not super easy content. But click history, that's a multinomial distribution. Basically, you have made 100 purchases, or you have written about 100 topics. And then you have probability for each of these topics, and the distribution of your item will be distributed in this way. So from my latent representation of the history, I can calculate the probabilities of all these items. That's this one. And then I have the variational distribution, which is my latent variables, to be distributed like that. So now I have basically three functions. I have the function for my mean of the distribution. I have a function for the standard deviation of my distribution. And I have this probability of the item history. And we will model all these functions as deep networks. And that's sort of what they did in the schema paper on variational autoencoders. It's funny that it's actually just a special case of the paper. They spend most of the time on the theory, but then this is the thing that has been picked up the most. Right, click history is multinomially distributed. So this is the theoretical way of describing this model. And then I have some deep neural network that is similar to that. So I start with my X vector, which is my click history, or my token history. And then I have some neural networks, some hidden layers that will estimate my mean and my standard deviation. And then I reproduce the latent representation of my click history. And then I put that back into a deep neural network that will reconstruct my click history. So the first part of this one is the decoder. And then the decoder ends up in my latent representation set. And that will be reconstructed as the decoder to my X. Okay. So that's basically the neural network structure of the same equations up here. Okay. I hope you're following. Otherwise, just ask.
Do you know if this would work with Gaussian distributions? So if you don't have like a click history, if you have another kind of data set?
If my X is Gaussianly distributed, you mean?
Yeah.
Yeah. No, that will probably work as well. So what the distribution that you assume that my X will follow ends up in your loss minimizing function, the loss that you want to minimize at the end of the neural network training. So it will just become a different functional form. And of course, the loss is very important. The functional form of your loss is important for how well your training is going to be. But I guess most of these equations might work for different distributions as well. But I think in the Kingma and Welling paper, I think they assumed X to be Gaussianly distributed as well. So, and that's not, the likelihood function is not the difficult part. It's the posterior that's the difficult part. So it's actually how your Z is distributed. That's very important. That's more important. Okay. So now let's look at some code. So I will create a PyTorch representation of the above network here. How many did some PyTorch code? Not that much. I guess TensorFlow is more popular if you did stuff like this. But it's very, it's very straightforward, the representation. You have some init function that will create the network for you. In my case, I start with a dropout layer on top, just for regularization. And then I have my Q network. That's the variational distribution, i.e. my encoder. And then I have to depend on how many layers I want. I will loop over the input parameters and create linear layers that depends on the depth of my encoder. And then for the optimizer to understand what parameters are available in the model, I need to append the parameters to a list of parameters I have. So that in the end, the optimizer will pick up, okay, these are the parameters in the model, and this is how I should backpropagate in this list of parameters. Okay. And then I have my decoder network, which is just the same thing. I invert the list. So in this case, I assume that the decoder structure is exactly the opposite of the encoder structure. So I just loop through the list of layers in the opposite direction and create linear layers for that one, which is this row, and add the parameters to my list of parameters. So that's basically the structure of my network. I have a softmax in the end because I want to normalize the probabilities of my multinomial distribution.
Just out of curiosity,
Mm-hmm.
you already explained this in the last meetup, but what's your reasoning for choosing PyTorch?
No. The last meetup we only did shallow machine learning, so no deep networks. Yeah, I don't know. I mean, I looked at TensorFlow and PyTorch. I mean, I'm late into the game here, so I had the opportunity of actually being able to choose, and I looked at some pieces of code, and I decided PyTorch looked nicer. Well, I mean, on the specs looks nice as well. Yeah. But I mean, in terms of GPU calculations, I don't know the technical details. Yeah, but I mean, from a Python user, it's easier to write PyTorch code compared to TensorFlow, which is more. So it's just for ease of use, basically. Okay, and now I have. So that's my network structure. Now I need to write the encode and the decode functions. So I start with the encode, doing some normalization of the input, and then I will loop through the layers and just multiply the matrices, apply my activation function. I'm using TANH because that's what they do in the Netflix Google paper. I didn't optimize this using some fancy genetic algorithm. And then we come to some interesting parts, which is basically how I estimate the variational distribution from being Gaussian. So now I take my last layer would be of some certain length, and I take the first half to estimate my mean of the Gaussian distribution, and then the other half to estimate the standard log of the variance. And I can recreate the standard deviation from the logarithmic variance and calculating something called Kullback-Leibler divergence. We will see the equations further down, but basically you have to calculate this using some statistics. It's nothing you can come up with yourself or change afterwards. It's part of actually the structure of the variational autoencoder. And I return the mu, the standard deviation, and the Kullback-Leibler divergence from the encoder. I continue to the decoder, which is just standard multi-layer perceptron. So I'll just loop through the layers and apply my activation functions. And the whole forward step is first, of course, encoding my click history. And then I will apply, okay, can skip this for now and go through the theory afterwards before doing that. But basically decoding as well, applying my softmax in the end. So that's my forward step. I'm just running through the network. So let's this row and this row up here is mystical right now. So let's see what's the reason for that. So basically, when you're training an autoencoder, variational autoencoder, you have to do something that you normally don't do in neural networks. I'm trying to optimizing a thing called the evidence lower bound, which is something you derive from the posterior distribution that I started with a little bit above. And I will not go into the details here because it will take far too much time. But basically, the thing is that I need to calculate two terms. The expectation of my log likelihood of the data given my latent representation, and the Kullback library divergence between the latent representation and the probability of my latent representation. And the first term involves my encoder. Sorry, I will probably mix these up a lot. And the other term involves the encoder. So that's sort of the important thing here. Then I will apply something called the reparametrization trick, because this one, if I want to do stochastic gradient descent on this equation, I have problems because my z variable is actually stochastically distributed, and I cannot easily apply backward propagation. So I need to solve this in some way. And I don't know if that's originally from the variational autoencoder paper or if it was already done before. But what they do is that they apply some trick to rewrite how Z is distributed using the fact that it's Gaussianly distributed. And this is actually why it's important that my latent representation is Gaussianly distributed. And I rewrite it as the mean, which is the output of the first half of my encoder network, and apply some stochastically distributed epsilon and multiply it with the standard deviance. Because now I have turned a stochastic component just into an epsilon variable, and I can derive or take the derivative of mu and sigma without having the problem of them being stochastic variables. And this is basically what we have to do in this step here. So this is just taking away the stochastic component into something that I can apply backward propagation on. Okay, let's go on. So now I see that I have the likelihood, the log likelihood from the elbow, and I have the Kullback-Leibler divergence, and I can sit down and calculate. I didn't do this. I just took it from the papers. And you can actually get some closed form of these functions. The Kullback-Leibler divergence becomes some function of the latent representation, and the final loss becomes the sum of the log likelihood of the data minus the divergence, KL term. And that's basically right. So that's just a reparametrization trick. Okay. So now I have my network. I need to do some training. Right. I have some note here about the difference between the training here from how you train normal collaborative filtering and how you train this network. So the important difference here is that you have as input the whole click history. So every row in my training data set will be the complete click history up to some point t. While when you train a standard matrix factorization model or collaborative filtering model, you actually do it on a user item level. And they claim in the paper that this is better because you, yeah, I mean, it's not clear that it's actually better.
What did you say was the loss function actually?
The loss function is my elbow, this term. And
can you understand this somehow? Does it measure like how much the X changed when it went through the whole network?
No, I think you can understand this as so this first term on the right-hand side represents your decoder network, how good your decoder network is in terms of how big the likelihood of the data is given your latent representation. And the other term is basically measuring how good your encoder is in terms of the difference between your variational distribution, i.e. your approximation, to how it's actually distributed. So that's how I think that it should be interpreted. Okay. So now I have to create my, from the data set I introduced above, I turn that into the right form for inputting into my network. And basically, I create a weights matrix that is of shape. This is the number of professors I have, and this is the number of tokens that are available that I have written about. It should be Bayesian, deep, neural, and so on. And the rows of this matrix is basically just how many times a certain professor has written about the topic. Okay, so I just take the first row, the first professor, he has written about the first token one time, and then a lot of zeros. So it's a very sparse data set. Since there are so many things to write about, and you don't have time to write about a lot of them. And then I tried to make a sparse representation of that data, and then I realized that PyTorch couldn't train on sparse tensors. That's something that is better with TensorFlow, I think. I set my batch size to 1,000. I experimented with this a lot. And then I create some data set loader in PyTorch. They have some function for handling the batching of the data automatically. And I shuffling the data. So for every batch, I shuffle from my main data set. And this is the train function in PyTorch. Oh, right. Here I have this one should actually be above here. I introduced the optimizer below here, which is wrong. No, it's just part of the function. So maybe it exists already. OK, whatever. I loop through my batches, and I run through the network. This is just going forward in the network. And I get back my the logarithm of my probabilities of my different clicks. Some other term I don't really remember.
If I can ask here.
Yeah, sure. Absolutely.
I don't know Python. Optimizing zero grad, is that the stopping condition?
No, it's just if I'm doing stochastic gradient descent, if I'm doing add a grad, if I'm doing ADAM, and so on. So at the end of the screen, I actually introduce the optimizer here, which ADAM optimizer on the parameters, and I introduced some initial learning rate to be this number. I run through the network forward, and I create the first term of my elbow, which is the negative log likelihood of the data. I introduce some regularization of the weights, which is something they don't talk about in the paper, but they do in the notebook. And then I calculate the elbow from the likelihood, the Kullback library divergence, and my regularization parameter here. Okay, and then I save these items because I'm interested in them. So I'm saving them in an array, and I'm running through network backwards. This is just loss function dot backwards. And then I'm running the optimizer with optimizer.step. And then I'm optionally writing some debug information if I'm interested in that. And that's the training of my network. So there's a lot of, if you did normal neural networks before, there's a lot of new stuff here because I'm completely different loss function because of the variational autoencoder structure of my network. And you have this stochastic component in the training that I will skip back. So we just repeat that. I'm actually sampling my epsilon here for every batch I'm running. So that's, I think, the most important differences from how to train this compared to a normal network.
It would be hard in TensorFlow, right, to do?
Maybe, I don't know. No, but I mean, they do it. So in the paper, the notebook they supply with the paper, they actually have a very similar structure like this. So I don't know the details about that. So I'm introducing my set the hidden layers to be my latent representation to be just of size 10. So my Z vector is just a 10-dimensional vector. I have another hidden layer which is of size 100, and then my input layer will be of the size of number of items because my X vector is the click history. Okay, and then I train. I train 11 epochs for some reason.
Adam or Adam?
Yeah.
What is that? Alternating direction? Or
No. So it's adaptive something. Yeah, because you actually introduce just a initial learning rate, and it will try to optimize the learning rate as the model is training. So it's actually an improvement on normal stochastic gradient descent, where the learning rate is fixed throughout the training. So, and the idea here is that this will increase the convergence time, because after a while, if you have a sort of a model that is just slightly improvement for every iteration, you actually want to improve the learning rates. You want to increase the learning rate. But if you have a fixed learning rate, this will just take a lot of time because you make small changes. Because the gradient is really small when you're doing small changes. So you want to amplify the size of the gradient when you have a network that is getting closer to convergence. Okay, so that's the idea here. And it's, there are so many versions of these Adagrad and Adam whatever. So it's a very active area of research, I think, because you want to improve the time of training of your model, of course. So I train 11 epochs. I think it was supposed to be 10, but then it's a typo. And now I can actually plot the results here. And it's plot per batch. And my batch size was 1,000. I had approximately 40,000 rows in my data set. So I train on about 500 batches in these 11 epochs. And I can see now how my elbow, which is my loss, the loss for the variation autoencoder, is decreasing. And we see that the loss is decreasing significantly in the beginning, and then it will flatten out and improve only slightly after each epoch. And the important part of this plot is actually the difference between the two terms that I had in my loss function. I had the likelihood of the data, and I had my KL term. And you see that the KL term is a lot smaller than the likelihood term. And only after a while I realized this. I trained my network and I didn't get that good results. I tried to understand why. And it seems like the difference between my data set and the data set in the paper is actually I have a lot sparser data. And the log likelihood was the multinomial loss is dominating completely here. So basically I can only train the encoder network and the decoder network, while my encoder is not training that well. So I seem to have a difference in magnitude between the two terms in my loss function, which is preventing the network to train that well. I think that's the problem here.
So did you use shuffle equals true?
Mm-hmm.
Why?
It overfits significantly if I don't shuffle. So if I shuffle, I get really crap. If I don't shuffle, I get super crappy results. So it's basically overfits on the data, and I get basically a random recommender. I don't have any intuition. Sorry. It's just a fact. But it seems like, this is my guess here, that I have a big difference between my decoder and encoder loss because of the loss function I'm using and the structure of my data. So one improvement here could be that I change actually the distribution of my x's from the set, so that I get a loss function that is more in balance between the decoder and the encoder. But since this is a meetup work, I don't have infinite amount of time to spend on it. I didn't do that yet. But anyway, I see that I have problems with my collaborative filtering model here, but I can anyway validate the model. So I create the validation set, and the validation set will be the complete click history, including my validation period. And I sort of infer from the network by running through the training data and calculating some classical recommender system metrics on that. So I have, for example, recall at k. So my recommender will pick the top k items that the recommender is estimating that you're likely to, in this case, write about or purchase or read newspapers, articles that I likely to read about, and check at my top k items, how many of those did you actually choose? So that's what I'm using my validation set for. And for recall, I will estimate this from the total amount of items that you have purchased, just as a normal classifier recall. And then precision at k will be, of the top k items I've chosen, how many of those did you actually choose? So that's sort of the precision of my recommender. And since I know how a random recommender did 1 or 2%, because that's what the result I got when I didn't shuffle, I have that sort of baseline to compare with. So I run the model through, the forward on the training set, and then I estimate precision and recall on my validation set, and I get some numbers. I have 17.5% recall and 22% precision. And I can compare that with the factorizing machines, which is the shallow recommender I did for the last meetup. And I see that I have better results at my factorizing machine, basically. So I have a precision. I'm actually cheating a little bit when I'm validating my neural network. So I should compare with this column, which is the validation set, including tokens from the training set. And you can see that I have 22% precision is basically the same, but my recall of the factorizing machine is much, much better. The big difference here is that my factorizing machines is actually a hybrid approach, so I could use features, which is not plain collaborative filtering. So I'm expecting it to be better because it's using more information. And the funny thing was that I actually got this result just half an hour before the meetup started. So for the last week, I got a lot worse results, which is why I started looking into the elbow and the KL terms and so on. But then I increased the batch size from 500 to 1,000. I think that's it. And then I improved a lot. So actually, I'm happily surprised because this model is dumber. And it's not using the same amount of information as I did with my factorizing machines. And I'm sort of getting results that are in the same order. So it's kind of good, I think. Yeah, that's it. Questions?
I have a question about the loss function. If
Mm-hmm.
you could scroll up to that.
Yes.
Was that function analytically solved for, or could you experiment with that?
You mean this function? Yeah, it's analytically solved for.
Okay.
Because I'm making an estimation. So this term is the log likelihood of the multinomial distribution, which is given in your statistics books. And this term, they calculate in the variation autoencoder paper because of the Gaussian approximation of your decoder.
I was thinking if you could play with that, because basically what that one says is how similar those two distributions are.
Mm-hmm.
Yeah,
yeah,
I was
exactly.
thinking if you could change that to other metrics, if you will, for comparing distributions to play around with. But
Yeah, so probably you can, because my intuition tells me that this is just a lot of fancy math to come up with some equations that I put into a neural network, and the neural network doesn't actually care about the math. So I have a lot of opportunities to actually change the functional form here. So I guess that's possible. I mean, whatever floats your boat. That's basically how to think about this.
I had to deal with the Kalb-Leiper divergence in the case of non-Gaussian data.
Mm-hmm.
And what worked for me was smoothing. So
okay.
I don't know how it can be implemented in this case.
No, I don't. Yeah. So the thing here is that you should integrate this, being able to integrate this integral. And I guess there is a lot of ways of approximating this integral. I mean, they just make the assumption to be able to calculate it analytically, but I guess you could approximate more here, or do some other estimations here, so I get some nice form of this integral with some parameters that I can tune, just as any other parameters of my neural network, for example. Yeah. Okay.
I have a question as well.
Yeah.
It's about recommended systems in general.
Mm-hmm.
So for this example, we had I think about 45,000 authors and 20,000 tokens.
Mm-hmm.
Are there any? Do you need to consider the dimensions of that matrix? Like.
Of course.
Yes. I mean, are there any like guidelines or things we should keep in mind?
No. I mean, you have, it's a little bit of moment 22. So the more data you have, the better your recommender will be, but also the longer time the network will take to train. And as soon as you reach a point where you cannot fit the data set in memory on a single machine, you have other problems as well. So, I mean, I guess you want as much data as problems, but you will also, will be problems with that. Is that answering your question?
I think so, yeah. I also like thinking, could there be a problem if we have like many more tokens than offers? Maybe it depends on how many tokens each offer produces, but
yes. So I think that's related to the sparsity of the data and problems you get from that. So I think my reason that I have problems training this net is because of the sparsity. So if I have fewer items, or the items were more commonly consumed for each author, for example, I will have the KL term will be bigger, and I will have it easier to train my network, for example. But I think it depends completely on the model that you're using. So I actually read stuff about people building not this stuff in PyTorch, neural networks like this, because to handle the sparsity problems, doing other kind of things to handle that. Yeah. I don't know what.
The Google paper, what kind of data set was it working?
It was on this classical recommender paper, which is movie ratings. Yeah, I don't remember the name of Movie Lens, I think it's called, which is 20 million movie, 20 million rows where people have watched different movies and rated them, or something like that. Yeah. It's a lot bigger data set, and it's very different structure.
You mentioned you got a big improvement when you increased the batch size. Do you think that was also due to the sparsity of the data?
Yes, probably yes. Yeah, I tried lower batch sizes and I had even worse results. Yes. Okay. More questions? Yes.
Did you get any topics for the recommend?
Yeah, I mean, in the old Meetup, I recommended some topics. We can look at them. But since I got so bad results from this model until half an hour before the Meetup, I didn't reproduce something funny. But I can show them later. But I mean, it recommended stuff like Bengyu should write about adversarial or stuff. Nothing surprising. Okay.
Will you try to make this approach also into a hybrid approach?
Yeah, so good question. I actually, when I started implementing this framework, I realized that this is very hard to extend to a hybrid approach because there is no natural way to introduce the features into the data set here. Either I can try to just put the features as part of my X vector and just make the decoder also encode the autoencoder represent the features, but I don't think that's a good approach because it will just make the problem much more complicated. I want to make it easier with features. And I don't see a natural way of extending this model in this sense. And I don't discuss it in the paper. So actually, I think this might be a dead end. But
could you add them maybe in the last moment just to the prediction or something?
Yeah, of course. I could put extra layers after, maybe, and have the autoencoder just representing. Yeah, maybe. Okay. Thank you for this. And just come and ask me anything about the stuff afterwards. I will share the notebook, maybe the code, maybe the data online somewhere. Thank you.
Thank you, Josef and Johan, and Meetup group, and thank you all for coming here. So I guess that's it for this evening, but you're welcome to stay and finish up the pizza and beer for a little while, within limits if you want.
Regarding the beer or the steak?
Both, I would guess both.
Thank you for hosting us, and thank you for the free food.
I'm not paying for it, so it's okay.